together to make up the square on the hypotenuse. 2. Again, when we want to describe the area of a circle, we, like the Egyptians, describe it by the formula pi r, where r is the radius and pi is a number which we can approximate in various ways. Depending on how accurate we want to be, there is no such formula in Euclid. The only statement about areas of circles is, circles are to one another as the squares on their diameters. This rather enigmatic sentence means in plain, slightly simplified, terms that the area of a circle C is in a fixed ratio to the area of the square S on its diameter. We could recover the usual statement if we called the ratio e pi 4, but that would not be in agreement with the whole use of the term ratio. In Euclid, a ratio, whatever it is not the same as a number, as we shall explain later. Confused? It is not surprising, and the elements, despite their prestige, have probably generated more confusion than any other Greek mathematical work among readers in the Islamic, medieval, and modern European worlds. How the ancient Greeks understood them is rather unclear to us. These examples should give some sense of the difference between Greek mathematics and our own, and this is a useful starting point, since our problems in understanding it help us to begin. With a historicist sense of difference. The classical works were using methods which are alien to us to achieve ends, which in the main, we no longer have. With this in mind, let us consider what we know of Greek methods, and how far conjecture, hearsay, and the like can help us. Exercise 4. What steps would be needed to deduce a formula for the area of a parallelogram from proposition I.35 above? For the problem of material. Acting as many inventors are known to have done in the case of their discoveries, they have perhaps feared that their method being so very easy and simple, would if made public, diminish, not increase public esteem. Instead, they have chosen to propound, as being the fruits of their skill, a number of sterile truths, deductively demonstrated with great show of logical subtlety, with a view to winning an amazing admiration, thus dwelling indeed on the results obtained by way of their method, but without disclosing the method itself, a disclosure which would have completely undermined that amazement. Rule 4. Our Greek sources, with much more material at their disposal than we have, had little difficulty telling stories of how mathematics developed, however inventive we might find them. By the 17th century, when Descartes wrote, it was a different matter. New translations of the ancient Greek writers clarified both their importance and the excessive difficulty of their work, in comparison with the algebraic methods which could be seen as an alternative. Never one to defer to any older authority, Descartes imagined the Greeks using easy methods of discovery, similar to his own prescriptions for solving problems, and then making the results look hard so as to mystify posterity. Drawing on hints in Greek authors, particularly Pappus, he opposed analysis to the classical Euclidean synthesis. His claim was that the Greeks had used analysis, as he would do in his own work, but destroyed the works in which it was used. By such arguments, he not only propagandized for his own work, but started the fertile genealogy of speculation about why the Greeks had chosen to do mathematics in such a strange way. The tradition of a scholarly history, which began in the late 19th and early 20th century with Paul Tannery and Sir Thomas Heath, had more respect for the Greeks and less of an axe to grind, but little more material to go on. In his pioneering work, Tannery described the problem of sources. These writings cannot teach us the history of science, they leave us ignorant about its origin, of its first developments, just as, since important works have been lost, they give us no way of gauging, without having recourse to conjectures, the direction of research in higher geometry and the level of understanding which was reached. The history of Greek geometry must therefore appeal to other sources. It must subject those sources to a methodical critique such as one applies in other similar cases. This is the aim which I have set myself. 3. It is enough to recall the classical Greek problem of squaring the circle, that is, constructing a square whose area is equal to that of a given circle. A great deal of work was expended on this in ancient times. Grossly misunderstood by some medieval writers, it is now, for reasons which are as much to do with our different perspective as with our greater knowledge, not a concern for mathematics. 4. The only exception was Heath's discovery of an unknown manuscript of Archimedes' The Method, published for the first time in 1906. This work, which will be discussed in the next chapter, in some ways confirms Descartes' suspicions. Although he has been criticized since for the way in which he used his often unreliable sources, Tannery was on the whole careful, and many of his successors have been less so. Writing before the Babylonian and Egyptian contributions had come to light, he saw the Greeks as the earliest known mathematicians, and as such particularly important. But even today, the importance and the difficulties of source material remain much the same. The works of Euclid and his successors have been classics for three major civilizations: their own, the medieval Islamic, and the modern European. They have the advantage of being readable, often accessible in libraries, and now, at least in extracts, on the internet, and clearly central to any history of mathematics, whatever reservations one may have about Eurocentrism and the role of the Greeks as overvalued. Europeans, their methods and discoveries have had a decisive influence. However, as Tannery pointed out, their study needs supplementing to give us a history, and the construction of such a history raises serious questions of method and approach. In the first place, Greek mathematics is supposed to have started in the early 6th century BCE. At this time, the Greek world consisted of what is now Greece, western Turkey, and a few colonies, particularly Sicily. However, there are no surviving mathematical texts earlier than the discussions in Plato's dialogues, and no substantial writings before those of Euclid, about 70 years later. By Euclid's time, the Greek world had changed completely as a result of Alexander the Great's conquests, and included what we now call the Middle East, and the center of learning had shifted from Athens to Alexandria in Egypt. While there are a number of substantial mathematical texts from Euclid onwards, there are still major gaps in the record before it comes to an end. About 600 CE, some works said to have been written or lost, and many well-known mathematicians have no surviving works, known or not. Here is a list, with dates, of the main important Greek mathematicians and one rather arbitrarily chosen memorable work for each, where known. Euclid, Archimedes, Ptolemy, and others wrote a number of works, some lost, some not. The table is simply there as a rough guide. An entry in italics means that the work have not survived. Second, as Tannery recognized, our sources for most of what happened are of two kinds. The first, of course, is the works themselves, the second is descriptive material about the works of mathematicians scattered among other writers. While Plato and Aristotle date from the 4th century BCE, the rest are over 500 years later, and are commentators with particular philosophical allegiances. They have often been treated, as they should be, with suspicion, but for much of the early history they are all we have. A particularly important source is Proclus, who, around 450 CE, wrote a commentary on Euclid's book I, prefaced by a general history of mathematics up to Euclid's time and an exposition of what, in general, the aim of the elements was. For a number of statements, Proclus is the only source, but besides his late date, his allegiance to Plato's philosophy and to later embroideries of it make him a source to be treated with caution. Third, all the works which exist are not, like the works of the Babylonians or Egyptians, contemporary documents. As in ancient Egypt, papyrus was used for writing, and it is extremely perishable. Manuscripts were copied and recopied over centuries, and the earliest surviving copy of Euclid's Elements is from the 9th century CE, over 1,000 years after the work was written. Worse, mathematicians see no need to respect a text they are copying if they can explain it or express its meaning more simply, and for some works the earliest manuscripts have certainly been edited in this way. This problem is not as serious as the others, but it exists. More interestingly, we know very little about what kind of people in the ancient Greek world did mathematics, and why. Archimedes wrote a few interesting letters to patrons and colleagues, but he gives no explanation of why mathematicians are engaged in their solitary activity, and, as Netz points out, the community he refers to is extremely small. And this, one would think, was at the high point of Greek mathematics. Most of the time, the mathematicians seem not to have left records describing their practice, their students, their aims, and thoughts about their work. In this respect, our situation is worse than for ancient Egypt, say, where mathematics, so far as we know, was done by a socially well-defined group of people for particular reasons. A useful start at profiling the world of Greek mathematicians is done by nets, but it is necessarily speculative. In general, if we want a good basis for writing the history of any activity, we would like to have documents which describe what the participants were doing, how contemporary observers saw it, and the general social setting in which the events took place. What we have for Greek mathematics is nothing like this. Rather, it consists of an impressive collection of major texts, less than 20 in number, with some more minor ones, and some late and unreliable stories. The material spans a period of 1,000 years or more. If we want to think about it in a historical way, how do we do so? More contentiously, one could ask, why do we want to? Without even attempting the second question, we should make a particular point about reconstruction, which is one of the few methods available for dealing with the first. Whenever the historical record is weak, one wants to fill in the gaps, supplementing slender materials with imagination so as to form an idea of what Boudicca's chariots were like, what was in the Holy Grail, or the identity of Jack the Ripper. In mathematics, we attempt a reconstruction of a particular form, briefly, to deduce an unknown proof from the fact that we are told that one existed. This can 5. In particular, Netz's conclusion that the number of Greek mathematicians over the whole recorded history was at most 1,000 gives the classic works, and in particular the Elements, a tiny readership. Unless one distinguishes a higher-level creative mathematician from someone educated well enough to read the basic works. Be illuminating, but, unless a document which confirms the reconstruction turns up, it must necessarily be provisional, leaving the field open for other competitors. 5. The Greek miracle. The king moreover divided the country among all the Egyptians by giving each an equal square parcel of land. And any man who was robbed by the river of a part of his land would come to Sesostris and declare what had befallen him. Then the king would send men to look into it and measure the space by which the land was diminished, so that thereafter it should pay in proportion to the tax originally imposed. From this, to my thinking, the Greeks learned the art of geometry. Page 21. What the Greeks discovered, the greatest discovery made by man, is the power of reason. It was the Greeks of the classical period, which was at its height during the years from 600 to 300 BC, who recognized that man has an intellect, a mind which, aided occasionally by observation or experimentation, can discover truths. Page 9. The problem of why Greek mathematicians wrote their works as they did tends to be framed as a problem of origins. There must have been some event, some discovery perhaps, which led to what is called the Greek Revolution, or Greek miracle, in mathematics. The quotation from Maurice Klein is a typical example. There is a case for using revolutionary language, on the analogy of the 16th century scientific revolution, and one might try to adopt a version of Kuhn's theory of scientific revolutions. An obvious difficulty is our ignorance of when or how it might have taken place. The Greek authors are not responsible for the idea that they were revolutionary, but that should not stop us from adopting it if it seems reasonable. The paradigm of doing mathematics for the known Greek authors is a different one from any which went before. The evidence that we have suggests that their predecessors and indeed contemporaries in Egypt and Mesopotamia were better at calculation, but quite unconcerned with formal proof. However, if we accept that there was a revolution, the study of its origin has been a very problematic one, and it does not seem well adapted to Kuhn's framework in which the idea of a scientific community who pursue normal science is an essential component. We have a good record of what could be called a scientific community in the ancient Near East, even if it may not have been much like our own, but our knowledge of such a community at the dawn of Greek mathematics is almost non-existent. Before the 1920s, and the publication of the Egyptian and Babylonian texts, it was universally believed that the Greek Revolution actually founded mathematics as a science, and hence, the first truly scientific discourse. The belief lingers on among those who, either because they wish to define scientific mathematics in such a narrow way that it excludes the sophisticated procedures of the Babylonians, or because they have an ideological investment in a Western origin, cannot accept the evidence that Greek mathematicians, however revolutionary, were transforming an earlier Middle Eastern practice. To take one example, an important French structuralist, Tradition adopts the hard science prescience distinction made by Gaston Bachelard in the 1930s, the so-called epistemological break which founds a science, see Bachelard 2003. In the 1960s, Louis Althusser. 6. One should always here remember how very fragmentary our sources are. Both Herodotus and Aristotle described mathematics as an Egyptian import, while Plato in his Laws, probably for propagandist reasons, claimed that the teaching of mathematics was better in Egypt than in Athens. However, the state of mathematics in Egypt at that time is unknown to us. For Marx gave a naive version, it is fair to say that the history of science was not his primary concern. And the tradition is still present in a more sophisticated form in the Archaeology of Michel Foucault, having described the stages of formation of a science as its discursive practice, from the lowest to the highest, he continues. Mathematics the only discursive practice to have crossed at one and the same time the thresholds of positivity, epistemologization, scientificity and formalization. Hence the fact that the beginning of mathematics is questioned not so much as a historical event as a principle of history, a geometry emerging suddenly, once and for all, from the trivial practices of land measuring. 188, 9. As Paul Ernest points out, has fallen victim to the popular myth about the origins of mathematics in Greece, and rather late in the day, it might be added. It was perhaps one of Kuhn's major achievements to question the simplistic division implied here between what is scientific and what is not, to make clear that there is not a single scientific practice founded once for all, and to exhibit science as subject to its own breaks, which cannot necessarily be described as straightforward advances or retreats. The idea of a revolution as founding Greek culture is by no means confined to mathematics. It has long been a central dogma in the history of Western culture that the Greeks, around the 5th century BCE, were responsible for the invention of the scientific method, philosophy, rational argument, democracy, and much more. That view has been recently challenged, at least in part, in works such as Martin Bernal's Black Athena, which argue that there was a close relation in culture and even in language between Greece and the Middle East, particularly Egypt. However, even if the changes which may have brought abstract rational thought into being are not specifically Greek, they are significant. G.E. R. Lloyd has done the best recent work in trying to describe them, and to distinguish a hypothetical before and after. Attempts at non-Kuhnian explanations have included 1. The introduction of alphabetic writing, adapted from the Phoenicians around the 8th century BCE, but probably only brought into general circulation sans militaire the transition from an oral to a written culture. 2. The invention of coined money, about the 6th century BCE. According to the Marxist thesis of Alfred Sohnrethel, this led to the abstraction of things from values, and hence to abstract thought in general, for a recent version see Seaford. 3. The institution of the city-state with its tradition of public political argument. This is the central thrust of Lloyd's books on the subject, although he is careful to avoid single thesis explanations. All of these theses may have some force, and it may, as in the case of the revolution of the 16th century, be necessary to think in terms of a combination of factors. Any means for deciding the question is almost completely lost in the fog of historical conjecture, but this has not stopped this particularly fascinating historical problem from being the subject of wild speculation. 7. For the controversy surrounding Bernal's theories, which is far from resolved, see for example, the website www. For several illuminating discussions of the Greeks, their innovations, and their possible indebtedness to others, see the articles by Bernal et al. 1992 collected in Isis, Vol. 83, pp. 554, 607. Or dogmatic assertion. To be more cautious, to insist as Lloyd does on how little we know, is to risk being found unexciting. To some extent the status of the revolution in mathematics is linked to the others, particularly philosophy. From a different viewpoint, though, mathematics could gain by being considered separately. In the first place, the innovations in mathematics were of a very specific nature and have led to quite particular accounts of the revolution, and in the second, to see mathematics as the product of a general revolutionary process makes it too homogeneous. 6. Two revolutions? We're certainly not the first to develop a complex mathematics, only the first to use, and then also to give a formal analysis of, a concept of rigorous mathematical demonstration. Greek mathematical deduction was shaped by two tools, the letter diagram and the mathematical language. So far, I have concentrated on the most obvious novelty in Greek mathematics, the use of an ordered sequence of deductions, which in Euclid appears to be from what is considered self-evident. This interpretation of Euclid is strengthened by Aristotle's prescriptions, for which see Fauvel and Gray 2h.1, page 93, 4. It is this revolution which is of interest to Lloyd, partly for the reason that his study concerns the wider field of rational discourse in Greek society, whether medical, philosophical, or mathematical, and his description of what was distinctive to the Greeks in the first quote is a good one. In the second quote nets, looking at the collection of documents we have as evidence of how a community worked throughout the Greek period, concurs in seeing what was distinctive about Greek mathematics as a unified practice based on a toolkit of argument about lettered diagrams. However, any search for the origin of this particular revolution, apart from general sociological speculation of the type outlined above, takes us back to the most unreliable parts of the commentator's story, to Thales and Pythagoras. Proclus claims, for example, that old Thales proved 6 results, one being that the base angles of an isosceles triangle are equal. In other words, if the triangle ABC has sides AB, AC equal, then so are the angles B, C. This would certainly be revolutionary if we had any reliable evidence. One should not discount the value of myth and late propaganda as historical source material. But it is, in the main, source material for what later Greeks thought about their origins rather than for what Thales did. The idea that such a fact, which Thales' predecessors could well have considered obvious, needed proving, and the attempt, whatever it might be, to construct a proof, would have marked Thales' geometry off from any earlier ideas of what geometry, traditionally, the measurement of land, was about. Speculation about what Thales did, which was once an acceptable part of Greek mathematical history, is now generally discounted as serious history. The same is true, if anything more so, for Pythagoras, who Proclus claimed founded pure mathematics. The scholarship of Walter Burkert in particular has established fairly conclusively that no mathematical discoveries can be soundly attributed to Pythagoras at all. That he did exist is a reasonable assumption, since he is referred to by Herodotus and Heraclitus not long after his time, but not much more can be said. With reasonable evidence that a revolution of some sort took place, we have no serious information on the state of affairs before or on what happened, only some idea of the situation some time after. Netz makes an interesting case for dating this first revolution to the time of Hippocrates, about 440 BCE. According to our evidence, mathematics appears suddenly, in full force. This is also what one would expect on a priori grounds. I therefore think mathematics, as a recognizable scientific activity, started somewhere after the middle of the 5th century BC. His arguments are persuasive, but in the nature of things can hardly be conclusive. However, as we have seen, there are more unusual things to be accounted for in Euclid, and in much of what followed, than the use of argument and diagram, and the introduction of such special features, which we could provisionally think of as the second revolution, is the one which has particularly attracted the imaginative historians. The evidence is still a mixture of gossip and inventive reconstruction, but there is more to it. Among the elements which need to be explained are 1. Euclid's avoidance of numbers in describing lengths, areas, and so on. 2. His use, notably in Book 2, of a geometric language for manipulating areas where his Egyptian or Babylonian predecessors would have used something more like what we call algebra, see the discussion of Proposition 2.1 in the introduction. 3. His theory of ratios, which are intended to replace numbers in contexts where these may not be fractions. Clearly, the most economical hypotheses to explain all this would be, first, that Euclid's practices were the result of a second mathematical revolution, and second, that this second revolution was, on Kuhn's model, the result of serious problems which arose in the original practice of rigorous mathematics which made it impossible to proceed. Both of these theses, originally put forward around 1910, are still widely believed in a revised form, We now need to examine the arguments for and against them. Exercise 5. How would you prove Thales' statement on isosceles triangles, and what assumptions would you need? 7. Drowning in the sea of non-identity. But betray me, said Neri, and you go the way of Hippasos. The acousmatic, I presume, said Wiley. His retribution slips my mind. Drowned in a puddle, said Neri, for having divulged the incommensurability of side and diagonal. So perish all babblers, said Wiley. And the construction of the regular dodecahedron, said Neri. Figure 3. The 5 regular solids. By the incommensurability of side and diagonal, Beckett means the fact, mentioned in our discussion of the Meno, that the ratio of a square's diagonal to its side 2 is not a fraction. But his pub classicists most probably came across their story not in its Greek original source, but in its popularization in the 20th century history of mathematics, that a secret or a scandal of the irrationals. This story, in some more respectable form, is still widely believed. The basic of fact is that Pythagoras founded a sect of initiates whose secret knowledge was at least partly mathematical. He is said to have taught that all is number, whereby number is meant whole number, and at the same time he or his sect attached religious magical importance to the regular solids. However, you cannot construct the regular solids, at any rate those which involve pentagons, without bringing in irrational ratios, see Appendix B. Both this, and the problem of the side and the diagonal, suggest a difficulty or, to put it more strongly, a scandal, for Pythagoras's supposed program. Because if all is number, then the ratio of the side to the diagonal should be the ratio of 2 numbers. There are stories in various late writers that this was kept secret by the Pythagoreans, and that the secrecy was broken. Iamblichus, a commentator of the late 3rd century CE, refers to Hippasos of Metapontum as a member of the Pythagoreans who was expelled and drowned at sea for revealing a secret, in one version, the construction of one of the solids, and in another, the nature of the rational and irrational. How far you accept this story, as Beckett's characters did, depends on your estimate of Iamblichus as a source, and he does not go out of his way to inspire confidence. The next step for 20th century historians was to deduce that the secret, or scandalous nature of the irrationals for the Pythagoreans extended to the Greek mathematical community in general, and that this accounted for their avoidance of measurement. The definitive version of this story was due to Hasse and Scholz in the 1920s. Speaking of a crisis of foundations for Greek mathematics, they used it to explain Euclid's use of proportions. Given that the Greeks were born geometers, as they are usually held to be, it must be concluded with certainty that after such a foundational crisis, they needed to construct a purely geometric mathematics. In such a mathematics we should naturally also come across a theory of proportions, in which no arithmetical parts remain. It is not accidental that they were writing at the time of Russell's paradox, when pure mathematics was experiencing just such a crisis. Extrapolating backwards, they read the anxiety of the ancient Greeks as a version of fin de siècle angst about mathematical certainty. Although the Hasse-Scholz thesis was criticized in the years which followed its appearance and never became the only accepted view, it has survived well, partly because it does explain the problems referred to above, and because it is easy to adapt and revise. The most recent sustained attack is by David Fowler. Fowler rehearses many arguments which are now standard, that Plato and Aristotle, who are the nearest to contemporary sources, refer to the irrational without in any way suggesting that it was a problem, that the subject is not even mentioned by Proclus, who is supposed to be summarizing an earlier history, that the time of the supposed crisis is also a time when many major mathematical discoveries were made, apparently without trouble, and that Iamblichus is notoriously inconsistent and unreliable. Fowler contrasts Aristotle's hard-headed assessment. A geometer, for instance, would wonder at nothing so much as that the diagonal should prove to be commensurable with Pappus' apparent confusion. The soul wanders hither and thither on the sea of non-identity, immersed in the storm of the coming to be and the passing away, where there is no standard of measurement, and concludes that the discovery was no more than an incidental event in the early development of mathematics. While his thesis certainly advances some useful arguments, It depends strongly on a particular reconstruction of how Greek mathematics worked in the pre-Euclid period, while it fails to deal with a feeling that what is unusual in the Euclidean approach must have come from somewhere. And despite all arguments against it, the discovery of incommensurability is still often thought to be the revolution in Greek mathematics, as opposed to the simple introduction of deductive method. Two of the contributors to Gillies consider it as such. Exercise 6. What is irregular about the 5 solids in Figure 3? Exercise 7. Why are there no others? 8 on modernization and reconstruction. Eudoxus's general theory of proportions, which, from our vantage, amounts to a theory of real numbers, resolved the anomaly that the discovery of several incommensurables had introduced into Greek mathematics. For example, the significant content of the proportion theory of elements V is almost universally acknowledged to be due to, in some form or another, though the explicit evidence for this is very tenuous indeed. Most everybody says that Eudoxus' aim and achievement in Book V was to handle incommensurable ratios. I do not know how they can be so sure. For example, there is nothing to suggest this in the elements. Today's history, while usually avoiding picturesque stories about drowning, still has to cope with the problem of presentism and that of reconstruction. Indeed, if we use the word a problem, it is because both have their uses, and the historian's difficulty is to decide when they are the right tools to reach for in the box. The case of Euclid 2:1 was already cited in the introduction. Those who consider it to be equivalent to the distributive law for multiplication are, one might argue, guilty of presentism. If Euclid had wanted to state the distributive law, he was intelligent enough to do so. In this case, the problem is complicated by evidence that informal Greek mathematics, continuing in the Egyptian tradition, did use precisely such a translation. See, for example, Heron. This means that we have two dividing lines to respect, between Euclid and his informal contemporaries on the one hand, and between Euclid and ourselves, on the other. All this is part of a proper respect for differing historical traditions. It makes the historians work harder, but no one said it had to be easy. A quite different example is provided by Euclid's theory of ratios in Book V. This complex treatment of a ratio can be successfully modernized so that Euclid's ratio translates as the modern concept of a real number. That this is possible has been taken to mean that the Greeks, specifically Eudoxus of Cnidus, invented the real number system over 2,000 years before its development by Dedekind in the 19th century. I have given an example of confident statement and scholarly doubt in the quotes at the beginning of this section. Apart from doubts about Eudoxus's role, the idea that he was concerned with what we call real numbers in any sense is unhistorical and is now out of favor, although the reasons for doubting it are complex. Attacks on such ideas appear in the works of Knorr, Fowler, etc. However, it is interesting that it is in the nature of mathematics that such translation can be done. It is not possible to make a similar translation of Aristotelian physics. Question. See if you agree with this statement, and if you do, try to explain what features of mathematics favored the translation. As for reconstruction, historians feel the need for it most particularly when a source refers to some mathematician's work, without indicating how the work was proved. One then proceeds to present a plausible version of how the proof must have gone, with the hope of throwing some light on the state of mathematics at the time, or of supporting a thesis about it. Here are two examples. 1. In Archimedes's The Method he states that the cone is the third part of the cylinder having the same base and height. He attributes the discovery to Democritus, though he did not prove it, and the proof to Eudoxus. Archimedes may conceivably have had access to the works of both Democritus and Eudoxus, supposing these to have been written down. In any case, the 9. One could also contrast the extremely complicated definition of equal ratios in Euclid V with Dedekind's, disappointingly a simple definition of a real number. Challenge is to reconstruct what the two did. The main fact known about Democritus is that he was an atomist, that is, regarded the universe as made up of atoms, and this has led to a great deal of speculation on his possible use of the infinitely small. For Eudoxus there is a more accepted reconstruction, based on the supposition that his work was much like Euclid's, A supposition which in turn owes something to Archimedes' passing remark. 2. In Plato's Theaetetus, Theaetetus claims that his teacher Theodorus was drawing diagrams to show that a square of 3 square feet was not commensurable, in respective side with a square of 1 square foot. This relates to the problem in the Meno for the square of 8 square feet. The idea is that the square root of 3 is not a fraction. Theaetetus claims that Theodorus continued with 5, 7, up to 17, and then for some reason could go no further. This has given rise to a great number of reconstructions of the method which Theodorus could have used, which would have worked for 17, but not for 19. Euclid's proof of the same result 10 is of no help. It is in his extremely difficult book X, and would work for any number you like. Again, it can be seen that mathematics is peculiarly susceptible to this kind of a history. A brilliant example is Fowler's, which gives a plausible version of how Greek mathematicians thought of ratios in the 4th century BCE, with a great deal of mathematics and scholarly apparatus to back it up, aside from giving a great deal of information on what we know for certain manuscripts, papyrus fragments, etc., about mathematics in Plato's time. Fowler constructs a detailed model of how it could have worked. Reviewers have been respectful, but have usually expressed natural reservations. 9. On ratios. It seems necessary to insert something here to clear up what, in classical Greek terms, a ratio was, even if the experts are not altogether agreed on it. Euclid's book V starts by saying that a ratio is something which two quantities may have. He then sets out a complicated criterion for two ratios to be equal. This was much disliked, when it was not simply misunderstood, by his Islamic and medieval successors. It is popularly believed that Isaac Barrow in the 17th century was the first mathematician. To understand the theory. Point 11. I have already given some simple examples. The ratio of the diagonal of a square to its side is 1, the golden ratio is another. A third is the ratio of circumference to diameter. And so on. Here, for the record, is the definition. It is a good example of what is really difficult in Euclid, and we shall leave it to you to spend some time thinking about its interpretation. Definition v.5. Magnitudes are said to be in the same ratio, the first to the second and the third to the fourth, when, if any equal multiples whatever be taken of the first and third, and any equal multiples whatever of the third and fourth, the former equal multiples alike exceed, are alike equal to, or alike fall short of, the latter equal multiples respectively taken in corresponding order. 10. That is, if x is a whole number but is not a square, then its square root is not a fraction. 11. For the medieval theory, see in particular Murdoch. In particular, Murdoch claims that the 11th century Islamic mathematician Al-Jayni did have a correct understanding of the Euclidean theory. This complex definition underlies the statement that circles are in the same ratio as the squares on their diameters. For example, you can do much more with ratios, and you need to. For example, if you increase the length of a rectangle by 1 ratio and its height by a second, then you increase the area by a third, and so you have a relation of ratios which is similar to multiplication. In the section Plato and the Meno, we saw that if side and height ratios were both what we would call 2, the area would increase by 2. For a full discussion, look at least some of Book V and Book X, which introduces a whole classification of different kinds of irrationals, up to fourth roots or immedials. The exact reason for much of this theory is still debated, but the underlying theory is more or less understood. A different take on ratios comes from astronomy, since it shows how they tie in with numbers. Suppose that y is the length of a year, and d is the length of a day. We need to know the ratio of y to d to have an efficient calendar, which all ancient and modern people needed. It complicates matters that days are not all of the same length, but let us neglect that, as many of the ancients did. Our first observation is that the ratio is greater than 365. We find this by using 365-day years and observing that the date of the equinox gets noticeably earlier, over a shortish period. We next introduce 1 leap year in every 4, and get a better result, a ratio of equals 1461 to 4. After a few hundred years, we find this is too big, and so on. If we are astronomers, we continue, as the Babylonians and later Greeks did, to find more or less accurate approximations for the length of the year as fractions, sexagesimal or other kinds, and construct our calendars accordingly. 12. But if we are philosophers, we may well think that there is a real length of the year, and that this fiddling with figures is beside the point. This, perhaps, is the meaning of Plato's statement in the Republic, which is often ridiculed, that one should study ideal stars and not simply what one sees. We shall therefore treat astronomy, like geometry, as setting us problems for solution, I said, and ignore the visible heavens, if we want to make a genuine study of the subject and use it to put the mind's native wit to a useful purpose. Socrates even draws on the example of the calendar which we have been looking at for his argument. Will think that the sky and the heavenly bodies have been put together by their maker as well as such things may be, but he will also think it absurd to suppose that there is anything constant or invariable about the relation of day to night, or of day and night to month, or month to year, or, again, of the periods of the other stars to them and to each other. They are all visible and material, and it's absurd to look for exact truth in them. That the lengths of months were variable had long been known by Plato's time, that the lengths of days were too, was perhaps a more recent discovery. And the reaction to these facts in the Republic is that they exhibit the failings of material stars and planets, as opposed to the ideal counterparts which were designed by their creator. If we put this together with the statement from the Philebus, which opens this chapter, we could conclude that the ratio is what the real mathematician uses in his kind of mathematics, while, in the other kind used by craftsmen, surveyors, and mere star watchers. 12. This is, it has been pointed out to me, an oversimplification of the way ancient calendars were constructed. However, perhaps it can serve as a guide to thought. Recourse is made to fractions of all sorts as approximations. It is hard to go further, and a concept like ratio shows the limits of the hermeneutic program. The understanding which underlies the concept has been well hidden in the nature of the texts we have. The best we can do is to try to understand the use and to guess at the ideas which lay behind it. Appendix A. From the Meno. SOC mark now the farther development. I shall only ask him, and not teach him, and he shall share the inquiry with me. And do you watch and see if you find me telling or explaining anything to him, instead of eliciting his opinion. Tell me, boy, is not this a square of 4 feet which I have drawn? Boy. Yes. SOC. And now I add another square equal to the former one? Boy. Yes. SOC. And a third, which is equal to either of them. Boy. Yes. SOC. Suppose that we fill up the vacant corner? Boy. Very good. SOC. Here, then, there are 4 equal spaces? Boy. Yes. SOC. And how many times larger is this space than this other? Boy. 4 times. SOC. But it ought to have been twice only, as you will remember. Boy. True. SOC. And does not this line, reaching from corner to corner, bisect each of these spaces? Boy. Yes. SOC. And are there not here 4 equal lines which contain this space? Boy. There are. SOC. Look and see how much this space is. Boy. I don't understand. SOC. Has not each interior line cut off half of the 4 spaces? Boy. Yes. SOC. And how many spaces are there in this section? Boy. 4. SOC. And how many in this? Boy. 2. SOC. And 4 is how many times 2? Boy. Twice. SOC. And this space is of how many feet? Boy. Of 8 feet. SOC. And from what line do you get this figure? Boy. From this. SOC. That is, from the line which extends from corner to corner of the figure of 4 feet? Boy. Yes. SOC. And that is the line which the learned call the diagonal. And if this is the proper name, then you, Meno's slave, are prepared to affirm that the double space is the square of the diagonal? Boy. Certainly, Socrates. SOC. What do you say of him, Meno? Were not all these answers given out of his own head? Men. Yes, they were all his own. SOC. And yet, as we were just now saying, he did not know? Men. True. SOC. But still he had in him those notions of his, had he not? Men. Yes. SOC. Then he who does not know may still have true notions of that which he does not know. Men. He has. SOC. And at present these notions have just been stirred up in him as in a dream, but if he were frequently asked the same questions, in different forms, he would know as well as anyone at last? Men. I dare say. SOC. Without anyone teaching him he will recover his knowledge for himself, if he is only asked questions? Men. Yes. SOC. And this spontaneous recovery of knowledge in him is recollection? Men. True. SOC. And this knowledge which he now has must he not either have acquired or always possessed? Men. Yes. SOC. But if he always possessed this knowledge he would always have known, or if he has acquired the knowledge he could not have acquired it in this life, unless he has been taught geometry, for he may be made to do the same with all geometry and every other branch of knowledge. Now, has anyone ever taught him all this? You must know about him, if, as you say, he was born and bred in your house. Men. And I am certain that no one ever did teach him. SOC. And yet he has the knowledge? Men. The fact, Socrates, is undeniable. SOC. But if he did not acquire the knowledge in this life, then he must have had and learned it at some other time? Men. Clearly he must. Appendix B. On pentagons, golden sections, and irrationals. The folklore has it that the construction of the pentagon were known to the Pythagoreans. When, or which Pythagoreans, is unclear, but by the time of Euclid the key steps were the following. 1. You need to construct an isosceles triangle ABC such that angles B and C are twice angle A. This is because these angles will then be, in our terms, 72, and angle A is 36, which is right for the star A, B, C, D, E. Figure 4 constructing a regular pentagon. The angles of the pentagon are 108, so angles like ADE are 36. Hence the triangle ABC has angles A equals 36, B equals C equals 72. Figure 5 the extreme and mean section, picture. CE bisects angle C, which is twice angle A. So the triangles ABC, AEC, ECB are all isosceles, so the lines marked X are all equal. The statement that EB, EA equals EA, AB now follows by using similar triangles and the various identifications we have. 2. To construct the triangle, you need to divide the side AB at E so that the ratio of B to AE is equal to the ratio of AE to the whole of AB. This is called dividing the line in extreme and mean ratio. More fancifully in the Middle Ages it acquired the name of the golden section or golden ratio. If we want to use algebra, suppose AB has length 1, and AE equals x, so B equals 1x, then 1x x equals x1. X equals 1x, which we would now solve to give x equals 0.618. This is obviously irrational to us, because of the 5 in it, but as usual we are not sure whether, or how, the Pythagoreans discovered the fact. Again, Euclid's proof is rather late in Book X. 13. Even this is simplifying. Euclid proves in Book X that what he calls an apotome is irrational, and in Book 13 that the golden ratio is an apotome. However, there is a simpler proof which is generally thought to be a probable reconstruction, as follows. If you have a ratio of honest whole numbers, say 42 to 15, then you can reduce it in steps, as follows. 42 15 is equal to 2 plus 12 15 15 12 is equal to 1 plus 3 12 12 3 is equal to 4. Ending with an exact whole number. At each stage, you have a remainder less than 1, you invert this at the next stage, and get a whole number and a new remainder. This is Euclid's way of finding the common measure, or greatest common divisor for two numbers, in the above case 3, which divides both 42 and 15. The process stops because the denominators of the fractions get smaller, and so must finally reach 1. You cannot do this with the golden ratio, because of the way in which it is defined. The equation 1x equals 1 plus x, which is equivalent to the one above, shows that the fraction procedure never stops. And indeed this can be stated geometrically, as even the Pythagoreans could have done. Exercise 8. Explain why the fraction procedure cannot terminate. Solutions to exercises. 1. I do not think it is quite obvious. Clearly the four sides are equal, since they are diagonals of equal squares. The other point to note is that all the triangles are isosceles. So all their small angles are just half a right angle, as we would say 45, and the angles at the corners of the figure, each being composed of two such small angles, are 90. This makes the figure a square. We have used the result on angle sum of a triangle, which does not work in non-Euclidean geometry, but then the idea of square becomes dubious anyway. 2. Diagonal is commensurable with side. It means that there is a line L such that the side S is a multiple, say QL, and the diagonal D is also a multiple, say P. L. Now clearly, the area of the square on S is Q times the square on L, and that on D is P times the square on L, and, by Pythagoras' theorem, the square on D is twice the square on S. So P is equal to twice Q, or, the square of the ratio of P to Q equals the ratio of 2 to 1. Check that all these implications go both ways. 3. The usual proof is the following. Suppose equals 2, we can assume that P and Q have no common factor. Then P equals 2 quetzales. It follows that P is even, and so P is even. Mirror. B. D. A. C. Figure 6. Idea of proof by reflection of a Thales theorem. So P equals 2R, say, and P equals 4R. Rewriting, for R equals 2Q, so Q equals 2R. Hence Q is even, and so Q is, but this contradicts the supposition that P and Q have no common factor. 4. This is vaguely formulated, and rather hard to make precise. It is clear from the proposition that the area of the parallelogram is equal to the area of the rectangle with the same base and height. To go further, and talk of multiplying base by height, you have to say what kind of numbers base and height are. The easy case is where the two have a common measure. If one is PL and the other QL, then it is not hard to show that the rectangle is PQ times the square of side L. To go further, you need the general theory of ratios. In theory, this would allow you to show that a rectangle of sides 2 and 3 was equal to one of base 6 and height 1, however, it is difficult, to say the least. 14.5. There are two questions involved. One is what is an acceptable simple proof, and the other is what proof might have been used by someone at a time when organized deductive geometry did not exist. Euclid's proof is quite complicated, involving extra construction lines. It depends on I.4, that if triangles ABC and DEF have AB equals DE, AC equals DF, and the angles A and D equal, then they are congruent. In theory, one could apply this to show that if ABC was isosceles, then it is congruent to itself, ABC equals ACB. In practice, it would be more natural to use properties of reflection, for example, that ABC is unchanged by reflection in a mirror which bisects angle A. However, any of these ideas are at the basic starting points of geometry, and one wonders what Thales and his contemporaries, if the story is true, would have considered a proof. 6 and 7. The property usually taken to define the irregular solids is that their faces are all regular polygons and all of the same kind, and that in a given solid S the same number of polygons meet at each point, or vertex as it is usually called. If we write to denote the solid whose faces are p-sided, with q at each vertex, then we have 14. Dedekind claimed in the 19th century that he was the first person to have proved that 2 3 is equal to 6, and this is commonly accepted. And each of p and q must be greater than 2, while the angles of a regular p-sided polygon are pi. The sum of the angles at a vertex is therefore pi. This must be less than 2 pi for the result to be a solid. From this, with a little algebra, pq a 2p plus 2q, or a 4. It is now clear that the combinations of which have been given are the only ones. There is much more on this in Coxeter, an excellent introduction to the subject, with information on its later history. 8. The process cannot stop, because when you invert x, the remainder turns out to be x again. So you cannot have a sequence of ratios with smaller denominators, from which it follows that x cannot be a ratio of integers. Supplementary problem. I have left you one of the most interesting and typical problems in the history of early Greek mathematics as a research problem to think about. This is known as Hippocrates' quadrature of lunes. It is a clever area calculation, supposed to have been worked out by Hippocrates of Chios before 400 BCE. You can find in Fauvel and Gray, and also some account of the transmission line, which makes its status rather unreliable. Consider 1. The result. 2. How its status is evaluated by various modern historians, accepted without question, or grudgingly, or set on one side as dubious. 3. How you would assess the importance of the result, and of its authority. 4. The problems about how Hippocrates might have arrived at it, and why. 3 Greeks, practical and theoretical. 1 Introduction, and an example. But, unlike Euclid, who attempts to prove musical propositions through mathematical theorems, Nicomachus seeks to show their validity by measurement of the lengths of strings. The leading Greek geometricians were all master carpenters. Euclid, the author of the Book of Principles, was a carpenter and known as such. The same was the case with Apollonius, the author of the book on conic sections, and Menelaus and others. The complaints of the previous chapter about the poverty of documentary evidence for Greek mathematics before Euclid need to be modified for the later period, say from 300 BCE to 600 CE. There is indeed a variety of material, but it is quite heterogeneous, and scattered in time and space. We are often vague about the dates of writers, and we have to guess about their communication, and still it seems that the survival of material is determined mainly by chance. Our first quotation describes the work of Nicomachus of Gerasa, whose arithmetical, philosophical, and musical works were treated as important in the Islamic and European Middle Ages, and so survived although modern authorities consider him a desperately poor arithmetician. At least, as the quotation shows, he sometimes had a practical approach which was quite different from what we consider typically Greek. The description of Euclid and Apollonius as carpenters runs contrary to all the information we have from other sources, but is it simply folklore? We have no way of knowing. How many ways were there, indeed, of being a Greek mathematician, and did they change over the 900-year period which we are considering? Did they interact? How did the Romans, generally portrayed as an uncultured master race with no interest in science, contribute to the way mathematics was done in the period when they dominated the Greek world? For if often we can say, at this time, mathematics was used in a different way from our own, the following methods were used, with the following ends in view, with the Greeks the situation is more complicated, and less well understood. The heritage which was passed on as important, particularly from the 16th century, was that of Euclid, Archimedes, and those who followed their models, axioms, theorems, and proofs. The ideology which went with it, which I have referred to in the last chapter as due to Plato, is that mathematics should not deal with the real world, or with applied problems. The reality is certainly more complicated, and even accepting that we have lost many records of carpenters, tax gatherers, architects, and engineers, which we must suppose existed, There is quite a complexity and variety in what remains, even if some of it is what appears to us rather low-level mathematics. H F D E C B A K. Figure 1 Menaechmus's construction. A and E are given, and it is required to construct B and C mean proportionals. The parabola is given by the rule, the hyperbola by the rule. df equals C and dk equals B. A good example of the interaction of theory and practice is provided, surprisingly, by the classical problem of the duplication of the cube. The problem seems to have surfaced sometime before 400 BCE in the form: given a cube C, to construct a cube D whose volume shall be twice the volume of C. Using an argument similar to the one I have given in Chapter 2, it is easy to see that, if the side of C is a feet, that of D must be a 2 feet, and to generalize from doubling to increasing in any proportion. This was done quite early. The earliest solution, by Menaechmus, is said to have involved the invention of the curves which we call conic sections. In modern notation, we would take a parabola whose equation is y equals x and a hyperbola whose equation is xy equals 2a. They meet at x equals a 2, y equals x. So far so good. See exercise 1 for a check that this solves the problem. We have not said how Menaechmus defined the curves, and the sources do not either. In later times, they were defined in the first place as sections of a cone. The information which is encoded in the equations I have given had to be proved, and was given its definitive form in Apollonius's Difficult Conics, one of the major works in the classical Greek tradition. However, there are doubts about whether such arguments were available to Menaechmus. The record which we have is related to the problem of 2 mean proportionals as in exercise 2, and looks more like the coordinate definition which we would use. Nor gives a reconstruction of how Menaechmus might have thought of it, with criticisms of earlier reconstructions by Heath and others. We have a substantial amount of information on the cube duplication problem, even if some of it is hard to interpret. One particularly interesting source is a supposed document by Eratosthenes, called the Platonicus, which only survives in quotation. Eratosthenes gives 1. In Eutocius' commentary on Archimedes' sphere and cylinder. Figure 2 The mesolabe. The triangular plate AET is fixed, while MZK and NHL move. To find 2 mean proportionals between AS and GL, slide the 2 plates so that the meeting points R and O are in a straight line with A and G. A folklore account of the origin of the problem. Though not reliable history, this at least has a practical appearance. He dismisses previous solutions, without describing them in detail, as impractical or unwieldy, and presents his own solution, by means of a machine called a mesolabe, or a mean taker, which can construct any number of mean proportionals between A and B, if properly calibrated. This immechanical solution in itself goes against the standard image of Greek geometry as purely abstract, and this is still further contradicted by Eratosthenes' claims that the method can be used in all sorts of ways. We shall be able, furthermore, to convert our liquid and dry measures, the meter tes and the medimnus, into a cube, and from the size of this cube to measure the capacity of other vessels in terms of these measures. My method will also be useful for those who wish to increase the size of catapults and ballistas. For, if the throw is to be increased, all the elements of these engines, the thicknesses, lengths, and the sizes of the openings, wheel casings and cables must be increased in proportion. There seems to be some much stronger link between theory and practice here, though nor warns. Eratosthenes was chiefly a man of letters, and one suspects that his vision of the practicality of a sensitive special-purpose instrument like the mesolabe was rather overstated. Still, the ideology behind its invention seems genuine. Nor may underestimate the extent to which at least some Greek geometers thought of the problem as applied. The same motive for the construction appears in the undoubtedly military work of Eratosthenes' near contemporary Philo of Byzantium. Here then, without straying outside the boundaries of a classical geometry, we find a mechanical solution to a problem which is at least being promoted for its practical uses. Clearly, and this is the point which we shall investigate in this chapter, the nature of Greek mathematics is more complex than one might have thought. We shall look at some examples of the later tradition which do not entirely fit into the Euclidean mold, including Archimedes, Heron of Alexandria, and Ptolemy. All were tremendously influential in the later development of mathematics, and all raise interesting questions about the varieties of Greek mathematics which were competing for influence over the long historical period which concerns us. At the same time, because of the length of the period and the variety of the work produced, it would be impractical in a book of this kind to try to cover everything. In particular, for the important work of Apollonius, Diophantus, and Pappus, you will have to look elsewhere. The remarks on sources made in the previous chapter apply on the whole. The major historian who has recently concentrated attention on the late period is Cuomo, to whose works and we shall return in due course. Exercise 1. Check that Menaechmus's construction does give a line of length a2. How would you generalize it to solve the problem of increasing the volume of the cube by a factor m? Exercise 2. Hippocrates of Chios showed that the general problem can be solved if, between two given lines A, B, with the ratio B, I equals m, one can construct two amine proportionals C, D, that is so that the ratios A, C, C, D, D, B are equal. Why is this true? 2. Archimedes. Archimedes is one of the most heroized figures in the history of science, but unlike Galileo and Newton, whose lives are available in minute detail, we know rather little about him. There is a growing literature on him, not so much biographical as an attempt to understand him from his works. True, his life is better documented than that of any other Greek mathematician, but that is not saying much. The chief sources tend to concentrate on a few memorable events, the Eureka story, his role in the siege of Syracuse, and his death at the hands of a Roman soldier. His works have always been seen as uniquely brilliant and difficult, and perhaps his portrait has been constructed to fit them, though unusually, there are letters introducing several of the writings which are personal, as not much else is in Greek mathematics. A late portrait of Archimedes as the absent-minded pure researcher is given in Plutarch's Life of Marcellus, and for whatever reason it has become influential. In line with a Platonic propagandist viewpoint, Plutarch claims that such practical considerations were unimportant to him. Yet Archimedes possessed so high a spirit, so profound a soul, and such treasures of scientific knowledge, that though these inventions had now obtained him the renown of more than human sagacity, he yet would not deign to leave behind him any commentary or writing on such subjects, but, repudiating as sordid and ignoble the whole trade of engineering, and every sort of art that lends itself to mere use and profit, he placed his whole affection and ambition in those purer speculations where there can be no reference to the vulgar needs of life, studies, the superiority of which to all others is unquestioned, and in which the only doubt can be whether the beauty and grandeur of the subjects examined, or the precision and cogency of the methods and means of proof, most deserve our admiration. It is not possible to find in all geometry more difficult and intricate questions, or more simple and lucid explanations. Some ascribe this to his natural genius, while others think that incredible effort and toil produced these, to all appearances, easy and unlabored results. No amount of investigation of yours would succeed in attaining the proof, and yet, once seen, you immediately believe you would have discovered it, by so smooth and so rapid a path he leads you to the conclusion required. One suspects that Plutarch had not read the works which he describes as smooth and rapid, since later generations have found them impressive but difficult. The geometrical core, which includes the measurement of a parabola and on the sphere and the cylinder, carries on, with great ingenuity, from the harder parts of Euclid. We shall not deal with them here, but there are good extracts in Fauvel and Gray. There is, however, more to Archimedes than these works suggest, and some of his other surviving works contradict Plutarch's image of the puro mathematician. The Statics and on floating bodies are the most serious works of theoretical physics, outside the framework of Aristotle's thought, in the Greek tradition, and as such, they had a great influence in the Renaissance, particularly on Galileo, see chapter 6. Further evidence of a mechanical tendency in Archimedes is provided by the strange document called the Method. Extravagant claims have been made for this manuscript, for example, that it contains a version of the calculus, and that the course of history would have been changed if it had not been lost. There is no need for such exaggeration. The method is, so far as we know, a very unusual work which had no imitators, and for good reason. In his introductory letter to Eratosthenes, Archimedes describes what he is doing, and why. Seeing moreover in you, as I say, an earnest student, a man of considerable eminence in philosophy, and an admirer, I thought fit to write out for you and explain in detail in the same book the peculiarity of a certain method, by which it will be possible for you to get a start to enable you to investigate some of the problems in mathematics, by means of mechanics. This procedure is, I am persuaded, no less useful even for the proof of the theorems themselves, for certain things first became clear to me by a mechanical method, although they had to be demonstrated by geometry afterwards because their investigation by the same method did not furnish an actual demonstration. The method referred to consists of measuring the areas of bodies by balancing them against simpler bodies, using a division into infinitely thin slices. For an example, two things are striking here. First, the use of weighing as a guide to understanding, presumably inspired by the work in the statics. This is the applied side of Archimedes, and second, the insistence, in the letter quoted above, that this is not a proof, but that a proof has to be constructed once you have found the answer. I should stress that the fact that the method is an applied work does not make it an easy read. If it had been, perhaps it would have been preserved and quoted more. To describe it as a lost is only partly accurate. Someone in the 9th century, and various others before that, must have known it and thought it of enough interest to be worth copying. However, it had no influence on the later traditions either through Byzantium or the Islamic world, so far as we know, and this although some Islamic mathematicians had a great respect for Archimedes and worked hard to reconstruct alleged works of his which they did not have. In contrast, one work of Archimedes had tremendous influence, and still does. This was his measurement of a circle. It is very short. It is thought that it is only part of a longer work of which the rest has been lost, but what remained was found immensely useful by much more simple-minded mathematicians. The 3 theorems which it contains are worth quoting in full, as a typically Greek way of approaching what we would call the problem of calculating pi. Proposition 1. The area of any circle is equal to a right-angled triangle in which one of the sides about the right angle is equal to the radius, and the other to the circumference of the circle. 2. Discovered by Heiberg in Istanbul in 1906, then lost again, but recently rediscovered, sold at Christie's for $2 million, and subjected to modern scientific reading methods. Proposition 2. The area of any circle is to the square on its diameter as 11 is to 14. Proposition 3. The circumference of any circle exceeds 3 times the diameter by a quantity that is less than 1/7 of the diameter, but greater than 10 parts in 71. It is clear that Proposition 2 is both wrongly placed and probably not as Archimedes stated it. This of course added to the confusion of medieval readers, who tended to go for the more usable Proposition 2, but at different times, all 3 parts were found useful. The first states that the area A is RC, where R is the radius and C is the circumference. The Greeks sometimes worried, as we would not, whether this implied the necessary existence of a straight line whose length was equal to the curved line C. The second states that A equals 1114. The third also gives the approximation 3 for the ratio of C to 2R, which is still used after over 2,000 years, and was gladly taken as the A right answer by calculators who had no use for Archimedes' more precise formulation. 31071 is C2 are less than 31.7. When we use the approximation 3 for pi, we are therefore indebted to Archimedes, although we probably know nothing of his methods. These were interesting in themselves, however, as an example of how he calculated, again, a more down-to-earth procedure than the Platonic model of mathematics would suggest. For the upper bound of 3, for example, he starts with a circumscribed hexagon. Archimedes assumes that any circumscribed figure has a greater perimeter than the circle, and proceeds to find successively smaller ones. By bisecting angles, he derives the rules for the lengths of successive sides, Rule 1, A, B equals A, B plus C. Rule 2, A plus B equals C. These two rules make it possible to find the perimeter of polygons with 12, 24, 48, and 96 sides as aids in calculation. He uses a fractional approximation for 3, whose origin is unexplained, but which is needed in the formula for the hexagon. By successive applications of the rule, gets a rather complicated fraction for the 96-sided figure, and shows that this fraction is larger than 3. All this is a very interesting mixture of Euclid-style geometry and computation with ratios of numbers. The way in which the fractions are written and manipulated recalls the technique of the ancient Egyptians. Unit fractions like rather than sexagesimals. There are repeated approximations to square roots which, while they seem correct, are not explained and so have been the basis for much speculation. All this is just what we claimed, perhaps prematurely. Greek geometry avoided the detailed engagement with numbers. This broad statement, true for Euclid, Apollonius, and the major works of Archimedes, is, as we will see, not at all true for a variety of others. Is the measurement of the circle intended as an aid for practitioners, or simply as an exercise in technique? We have no indication. And while Archimedes is always using the numbers as ratios, not as absolute measures of length, the way is open for land measurers to use them in other ways. 3. See Chapter 6 for Kepler's attempt to construct an infinitesimal version, around 1600. Figure 3 regular hexagon circumscribed about a circle. Figure 4 picture for exercise 4. Exercise 3. Show that the perimeter of the circumscribed hexagon is 4,3r. Exercise 4. Rule 2 above is clearly Pythagoras's theorem. But where does Rule 1 come from? 3. Heron or hero. 3 centuries after Archimedes, a very different mathematician left a number of works which were both accessible and popular. This was Heron, or Hero of Alexandria. His works are not easy to find, except in small extracts, but they are numerous and quite astonishingly diverse, dealing with theory and practice sometimes separately and sometimes together. That he was not despised, despite his practical bent and what some historians have seen as weak mathematical attainments, is shown by Pappus's description of his work, or that of his school, which in turn suggests influence. The mechanicians of Heron's school say that mechanics can be divided into a theoretical and a manual part. The theoretical part is composed of geometry, arithmetic, astronomy and physics, the manual of work in metals, architecture, carpentering and painting, and anything involving skill with the hands. The ancients also describe as mechanicians the wonder workers, of whom some work by means of pneumatics, as Heron in his Pneumatica, some by using strings and ropes, thinking to imitate the movements of living things, as Figure 5 Heron's slot machine. Heron in his automata and balancings. Or by using water to tell the time, as Heron in his Hydria, which appears to have affinities with the science of sundials. The combination of quite classical geometry and detailed machine construction makes Heron interesting, unusual, and hard to classify. Predictably, his machines attract considerable interest on the internet, notably the earliest description of a slot machine. However unmathematical this may be, it is worth including to illustrate the variety of mathematicians' interests. Sacrificial vessel, which flows only when money is introduced. If into certain sacrificial vessels a coin of 5 drams be thrown, water shall flow out and surround them. Let ABCD be a sacrificial vessel or treasure chest, having an opening in its mouth, A, and in the chest let there be a vessel, FGHK, containing water, and a small box, L, from which a pipe, LM, conducts out of the chest. Near the vessel place a vertical rod, NX, about which turns a lever, OP. Widening at O into the plate are parallel to the bottom of the vessel, while at the extremity P is suspended a lid, S, which fits into the box L, so that no water can flow through the tube LM. This lid, however, must be heavier than the plate H, but lighter than the plate and coin combined. When the coin is thrown through the mouth A, it will fall upon the plate H and, preponderating, it will turn the beam OP, and raise the lid of the box so that the water will flow, but if the coin falls off, the lid will descend and close the box so that the discharge ceases. His geometry, the metrics, is both inside and outside the mainstream Greek tradition, giving rough rules for how to compute combined with Euclidean proofs on occasion. The most famous example, although not a typical one, is what has become known as Heron's formula for computing the area of a triangle given its sides. The formula is very unusual in Greek mathematics in that it requires you to multiply 4 lengths and take the square root. While you could think of the product of 3 lengths as a volume, the product of 4 has no meaning in Greek terms, and Omar Khayyam was still dismissing such ideas 1,000 years later. All the same, the formula became widespread and popular in Islamic and medieval times, and a tradition claimed that it was originally due to. For, Pappus does not note that an accurate water clock, compared with a sundial, would show the variation in the length of solar days, but this is not surprising, since elsewhere he criticizes water clocks for their inaccuracy. The variation is derived by Ptolemy purely on theoretical grounds, see below. Archimedes. If this is true, it shows Archimedes as innovative in a more striking way than had been thought. What Heron's work shows, perhaps more than any other, is the existence of traditions which we do not otherwise know about, and this is a warning against easy generalizations on the nature of Greek mathematics. The quotation from Pappus does suggest that he was considered special at least in his interest in machines, but it is unclear how much should be built on that. Many of the machines which he describes, such as water clocks, were certainly not of his invention. In parts of the Geometrica, he solved some quadratic problems by the Babylonian recipe. And this is taken by some scholars as a reason to fit his work into a genealogy which stretches from the Babylonians through to the Islamic algebraists of the 9th century CE. However, he is also capable of advising intelligent guesswork and using what appear to be quite new methods. The following example is again unlike our usual idea of Greek geometry. In a right-angled triangle, the sum of the area and the perimeter is 280 feet. To separate the sides and find the area, I proceed thus: always look for the factors. Now 280 can be factored into 2.140, 4.70, 5.56, 7.40, 8.35, 10.28, 14.20. By inspection, we find 8 and 35 fulfill the requirements. Note that the problem is not a well-posed, by which I mean that it can have numerous solutions. As an equation, it is a plus b plus a plus b plus 1 2 of equals 280. And of course the key point is that, for a nice solution a2 plus b2 must be a square, itself a favorite problem. It could be seen as an extension of the Babylonian problems which give you the side of a square plus its length, but it is considerably harder and more geometrical. Heron's solution continues. For take 1/8 of 280, getting 35 feet. Take 2 from 8, leaving 6 feet. Then 35 and 6 together make 41 feet. Multiply this by itself, making 1,681 feet. Now multiply 35 by 6, getting 210 feet. Multiply this by 8, getting 1,680 feet. Take this away from the 1680, leaving 1, whose square root is 1. Now take the 41 and subtract 1, leaving 40, whose half is 20, this is the perpendicular, 20 feet. And again take 41 and add 1, getting 42 feet, of which the half is 21, and let this be the base, 21 feet. And take 35 and subtract 6, leaving 29 feet. Now multiply the perpendicular and the base together, of which the half is 210 feet, and the 3 sides comprising the perimeter amount to 70 feet, add them to the area, getting 280 feet. This calculation is completely enigmatic as it stands. We can see that Heron's answer is correct, but what is he doing? Thomas's translation gives a good explanation related to the formula of Appendix A. In fact, if r is the radius of the inscribed circle, and s equals is half the perimeter, then the area is SR, and so the sum of perimeter and area is S. We can therefore look for factors, as Heron says, and guess s equals 35, 2 plus r equals 8. One could go on to ask how exactly, without algebra, such a procedure could have been hit upon. Such mathematics could be thought of, in the language of Heurup, as subscientific, short on proof, although the numerical check is given, perhaps designed to display skill and virtuosity rather than to be of any use. And yet the relation to the formula of Appendix A ties it in with a real geometry. Sometime later than Heron, probably, the dates of both are in dispute. Diophantus invented an algebraic notation which might have made such questions easier, but although his works were studied and commented, they had no apparent influence on the solving of everyday puzzles for more than 1,000 years. Exercise 5. Show that, in a right-angled triangle with short sides A, B and other notation as above, are equals. Explain what Heron is doing in terms of this formula. For astronomy, and Ptolemy in particular, mathematicians sometimes have difficulty in thinking about astronomy as a part of their subject. However, historically it is essential. Unified as a subject of study with mathematics from very early times, it has often provided work for mathematicians and motivation for much of their inquiries. The trigonometric functions and the study of geometry on the sphere owe more to the study of the heavens, at least in their beginnings, than to the geography of the earth. There are considerable problems, touched on lightly in the last chapter, in setting up a mathematical astronomy. One could list some of them. Find the length of the day. Find the length of the year. Before doing either of these, find a reliable way of measuring time. Find the path of the sun in the heavens, at a given place, at a given time of year. It is worth taking time to think about these problems, and what instruments, observations, and/or calculations you would need to answer them. All of them are non-trivial, and all need to be understood with some finesse before we can begin to answer the subtler questions about the paths of stars, planets, and so on, let alone eclipses of the sun and moon. Necessarily, a great deal must already have been worked out for Plato to pose the problem of accounting geometrically for the motions of the various heavenly bodies. The restriction classically put on these was that they must be composed of uniform circular motions. We shall see later what this implied. The restriction had a practical advantage and a philosophical one. The explanation, as I mentioned in the previous chapter, had to be descriptive, giving you the possibility of predicting where a body would be at a given time. This, incidentally, made it essential for astrology, which has almost always been a major concern for astronomers and by extension for mathematicians in general. On the other hand, there was no call for a physical explanation of what force might make the heavenly bodies move. This theory, which is not easy to reconcile with the descriptive one, was given by Aristotle and does not really concern us. The major textbook of astronomy which has survived is the work of Ptolemy, who worked in Egypt in the 2nd century CE. While he named it the mathematical syntaxis, from the time of the first Arabic translations it came to acquire the name Almagest equals Arabicized Greek. 6. Specifically, until the Renaissance. Hypatia among the Greeks and Custa ibn el-Yucca among the Arabs are known as students and commentators of Diophantus, and half of his work only survives in ibn el-Yucca's translation. 7. Whether or not one believes in the influence of the planets' positions at a given time, the actual calculations which determine them are often quite hard mathematics. Ptolemy, in his handy tables, simplified the work so that the practicing astrologer could look up the answer without reading his heavily theoretical Almagest. Almagest I, the greatest, by which it is usually known. Like Euclid, it was a standard textbook for over 1,000 years, much commented and occasionally revised and criticized in the light of new theories, but only losing its popularity in the 17th century as the theories of Copernicus, Kepler, and Newton came to form a solid alternative of a very different kind. Ptolemy was not the first to develop the theory found in his book. The ideas on how the planets move were supposedly first framed by Apollonius and dealt with in a textbook by Hipparchus, but their works, superseded by the Almagest, have not survived. What Ptolemy apparently added to Hipparchus was more accuracy and a simpler method of calculation. His book, however, though a major primary source and very interesting, is not a straightforward read, and this also is worth thinking about. Where a mathematics textbook typically has one general subject, and starts from first principles to show you how to solve quadratic equations, or prove Pythagoras' theorem, or differentiate, an astronomy textbook has to set up a large and complex apparatus of general theory, observation, and particular verifications, and this is true of Newton's Principia Part 3 as much as of Ptolemy. In the Almagest, Ptolemy first goes through the foundational assumptions, that the Earth is spherical and fixed in the middle of the universe, that the heavens move in circles around it, and so on. At this point, we have to set aside the fact that we know that Ptolemy's system is wrong, since it is in fact an extremely good mathematical explanation of what is observed, and the mathematics is what should concern us. So we must accept these assumptions. We then observe that the stars have two motions. In a day they describe circles about the pole star, and in a year they describe circles about a different axis, defined by the path of the sun, the ecliptic. Figure 6. The relation between the Earth, the poles, the equator, and the ecliptic in the geocentric model. A. B. O. RR 5 Figure 7. The chord of an angle. If theta equals angle AOB equals 2 phi, then the chord CRD equals AB equals 2 r sin phi in our terms, where normally r equals 60. Again, we would say that one is caused by the daily rotation of the Earth and the other by its annual rotation around the Sun, but that is not how it looks to the naive observer. Having got this far, Ptolemy needs to calculate the angle between the two axes, and this leads him into trigonometry or the theory of calculations about angles. The function which he uses is the chord of the angle, which modern translators usually write CRD theta. It is the chord in the sector of the circle whose angle is theta, so CRD theta equals 2 r sin, where r is the radius. The angle is written in our modern units, while the chord is written in units of length, in a circle whose radius is 60, using sexagesimal fractions, as for the angle. This again is interesting. We saw Archimedes calculating with Egyptian-type fractions for the circle, and this may have been usual, but for setting results out formally in a table, which is what Ptolemy did, sexagesimals are clearly better. They point forwards towards modern decimal notation, as well as backwards to Babylon, and they were to be used in astronomy continuously until recently. The table of chords is worked out fairly quickly using some basic Euclidean geometry, with some results of Ptolemy's own. Square roots are often extracted, as they need to be, with no indication of how, but we might suppose that something like the method Heron uses for finding 720 is being used. Next, Ptolemy describes an instrument for measuring the angle between the two circles, the ecliptic and the equator. He derives the angle from his measurement, using the table of chords, as 23, 51, 20. We therefore think of the Sun as moving around this circle at a uniform speed through the 12 signs of the zodiac, in one solar year of around 365 days. We can then find where the Sun will be at any time on any day of the year, and in particular, which sign it will be in. The problem is that, as seen from the Earth, the Sun does not move through the signs at uniform speed. The 90 from spring equinox to summer solstice, for example, takes 2 days longer than the 90 from summer solstice to autumn equinox. The Sun is slower in traveling through Taurus than through Leo. This anomaly, one among many astronomical anomalies which have to be explained, could be dealt with by supposing that the Sun actually had a variable speed, and finding how it varied. This was Kepler's idea, arrived at around 1600, and it is what one would say today. But, both for ease in calculation and because of the general theory, Greek astronomy did not work in that way. Instead, Ptolemy puts forward two models of how the Sun moves. They are, as he says, equivalent, but that is not really important, since the aim of an deferent Figure 8. The epicycle model. The planet moves clockwise round a small circle whose center moves anti-clockwise round a large circle centered on the Earth. This explains why some planets sometimes move backwards in relation to the stars. Explanation is not so much to say what really happens as to give an accurate description from which you can make predictions. Again, the physics, as we would call it, is not considered. In the first model, the Sun moves at constant speed round a small circle or epicycle, and the center of the epicycle itself moves at constant speed round the ecliptic, with the Earth as center. The second supposes that the Sun is traveling at uniform speed around a circle, but that the Earth is not the center of the circle. It follows that the sun appears to be traveling more slowly when it is further from the Earth than when it is nearer. In Appendix B, I give the detailed working out by Ptolemy, from his observations, of where the center of the orbit is in relation to the Earth. This is a detailed piece of Greek numerical mathematics, based on the geometric tradition. Is it practical? Very much so, in that it makes possible the calculation of where the sun will be. But it is supported by a formidable theoretical apparatus of results about chords in a circle, angles, and so on. Considered as a whole, and this is the justification for devoting so much time to his work, Ptolemy's Almagest gives more of an impression of the range and variety of Greek mathematics than any other text which we have. Exercise 6. Show that CRD equals 60 and CRD equals 62. Exercise 7. How would you find CRD given CRD? Exercise 8. Explain the variation in the sun's apparent speed on the eccentric hypothesis. Research problem. Find the 2 reasons why the length of the day varies as we would understand it. As Ptolemy would have put it. 5 on the uncultured Romans. With the Greeks, geometry was regarded with the utmost respect, and consequently none were held in greater honor than mathematicians. But we Romans have delimited the size of this art to the practical purposes of measuring and calculating. The above quotation heads Serafina Cuomo's chapter on the Romans, and her recent book makes the first serious attempt to investigate and indeed question a view of their mathematics accepted. Since Cicero's time. Briefly, this is that the Romans, in contrast to the Greeks, made no contribution to mathematics, and that any works of theirs which contain or use it, such as Vitruvius' architecture, are trivial in comparison with the Greek achievements. The charge has some basis in fact. As Cuomo acknowledges, I would be hard put to adduce a Latin equivalent of Euclid, Archimedes, or Apollonius, she admits. This seems like an understatement. Where are the Latin equivalents of Heron or Nicomachus? True, these second- or third-rate mathematicians worked under Roman rule, and may have been, like St. Paul, Roman citizens. However, they wrote in Greek, and in a tradition which was, and continued to be, overwhelmingly Greek. The Romans, with better access to the Greek classics than the 9th-century Arabs or the Renaissance Europeans, never seem to have felt the same need to build on their work and develop it. And while Cuomo also interestingly makes a historicist point about the class angle contained in Cicero's statement, one is still left with an underlying feeling that it is an ideological statement based on good factual evidence. The most interesting part of her argument is a broader one, and does bear serious consideration, that the practice of mathematical methods of some sophistication pervaded the Roman world from top to bottom. Some of her examples, notably the charioteer whose tomb boasts that he drove chariots for 24 years, ran 4,257 starts and won 1,462 victories, 110 in opening races. In single-entry races he won 1,064 victories, winning 92 major purses, 32 of them at 30,000 sesterces. Tr. and Lewis and Reinhold 1990, pp 146, 7. Testify to the power of a numbers to impress rather than to the ability to do anything with them. However, her study of the practice of the despised land surveyors, and of Vitruvius show how an appreciation and application of classical geometry underlay their practice. Perhaps rather than decrying the low level of geometry present in Vitruvius's architecture, we should think about the fact that it was a Roman, rather than a Greek, who bothered to write such a treatise. The architects of Greek temples were not, it would seem, given to exposition. We have different cultures with different ideas of what a book is for. Similarly, the famous tunnel of Eupolinus in Samos, dated at 550-530 BCE, is often cited as an amazing example of very early practical Greek geometry. How did the builders of the tunnel, who started from the 2 sides of a mountain, contrive to meet so accurately in the middle? The answer is again that we do not know, and no Greek sources seem to have taken the trouble to explain how such a recurrent problem could be solved. The Roman surveyors, however, organized as a profession in which a discipline was transmitted by means of textbooks, both explained how they did it and wrote instructions whose foundation is in their training in some derivative of Euclidean geometry. This debate is only now beginning. The same applies to the doubts which Cuomo has cast on the idea that Greek mathematics was in decline from the time of Ptolemy, if not before. It is not so much a question of rehabilitating the Romans. Rather, as we saw in Chapter 1 with the pre-OB periods, it is a question of looking at practices. 8. See Cuomo for a surveyor's account of how he helped the weeping villagers whose tunnel had manifestly gone badly wrong, which have been dismissed as trivial or non-mathematical, and seeing if they do in fact belong in our history, and if so, where. 6. Hypatia. Hypatia, the daughter of Theon the mathematician, was initiated in her father's studies. Her learned commentaries have illuminated the geometry of Apollonius and Diophantus, and she publicly taught, both at Athens and Alexandria, the philosophy of Plato and Aristotle. In the bloom of beauty, and in the maturity of wisdom, the modest maid refused her lovers and instructed her disciples. The persons most illustrious for their rank and merit were impatient to visit the female philosopher. And Cyril beheld with a jealous eye the gorgeous train of horses and slaves who crowded the door of her academy. Hypatia was born in the later part of the Roman Empire, an era when women were not free to pursue careers. This was a time when orthodox belief effectively wiped out centuries of scientific discovery. Ancient Greek works were torched and scholars were murdered. Hypatia was the last proprietor of the Hellenic age wonder, the Library of Alexandria. She is portrayed as a young adult facing the issues of a changing world. The reader will discover uncanny parallels to many current situations within the United States and, indeed, the world. Hypatia, a real, historically documented heroine, is a find for today's young adults who are searching for strong, non-fiction role models. Mathematicians, like engineers and physicists, have very rarely been women. The rarity is far more serious than for poets and painters. As a result, the study of a women mathematicians faces a serious difficulty in even getting off the ground, since there has until the 20th century been no continuing tradition from which to construct a history. The feminist historian therefore necessarily points out the existence of numerous such women of whom we know little or nothing, and attempts to weave the major lives of which we do know something into some kind of thread. The philosopher and mathematician Hypatia, who was stoned to death by a Christian mob in 415 CE, is the most important early, perhaps the founding figure for the tradition. And the questions which surround her life and activity may illustrate the wider problem. For if one were to take any other figure from Greek mathematics as a representative of something, generalizations based on the little that is known of their lives would be hard, although the works at least give some basis for building theories. With Hypatia, the difficulty is the opposite one. Her life is unusually well documented, in the general context of Greek mathematics, as the result of friendly and hostile accounts by later Christian writers. Most particularly, her devoted pupil Synesius, bishop of Cyrene in Libya, wrote a number of letters to her and about her which give substantial detail about her life and teaching, if from a particular viewpoint. On the other hand, although her ability as a mathematician is well documented and at least the titles of some works have been preserved, there is no extant text attributed to Hypatia, no Hypatia's theorem, no discovery which tradition assigns to her. With Heron, as was noted above, we know the works but nothing of who he was. With Hypatia, it is the other way round. On her life and her philosophy, for which the sources are good, Maria Zielska's monograph is a recent excellent source. Zielska begins with an account of the myths which have built up around her as an iconic figure since the 17th century, and which my opening quotes illustrate. She was a victim of Christianity and symbol of the death of the ancient learning at the hands of the new ignorance. A feminist icon and precursor of Marie Curie, a symbol of the imposition of European rule on Africa. Zielska produces a convincing picture of Hypatia as an influential teacher of mathematics, astronomy, and Neoplatonic philosophy to a circle of initiates, both pagan and Christian. Around their teacher, these students formed a community based on the Platonic system of thought and interpersonal ties. They called the knowledge passed on to them by their divine guide mysteries. They held it secret, refusing to share it with people of lower social rank, whom they regarded as incapable of comprehending divine and cosmic matters. Hypatia's private classes and public lectures also included mathematics and astronomy, which primed the mind for speculation on higher epistemological levels. She shows Hypatia becoming involved in a power struggle between factions in Alexandria in the years following 410, which led to a witch hunt, and eventually to her death. There was, indeed, a careful line to be drawn in late Roman times between the praiseworthy pursuit of geometry and the damnable art of astrology. See Cuomo, and Hypatia was probably not the only scholar to be caught on the wrong side of the line. Zielska further establishes, fairly convincingly, that her age at the time was about 60, and points out that her death was far from marking the end of learning in Alexandria, or the Greek world generally, or even of paganism. Pagan religiosity did not expire with Hypatia, and neither did mathematics and Greek philosophy. She also unearths a number of other references to women in the late Greek philosophical world, which show Hypatia's example to be not so unusual as had been thought. This is helpful, but of course the historian of mathematics would like to have more, and here as so often we enter the world of more or less ingenious conjecture. As Gibbon states, her father was the mathematician Theon, who has not been highly estimated in recent times. However, like many others of the period, he studied and commented the difficult works of his predecessors, and edited the text of Euclid in a version which was almost the only one to survive. The titles of several of Hypatia's works, mainly commentaries, for example, on Ptolemy and Diophantus, are known from later bibliography, and Synesius, her student, was a philosopher not a mathematician, and by the time when Islamic scholars recovered and translated Greek works, none of them bore her name. The scholar who wishes to study her as a mathematician, supposing it possible, has to use a certain amount of imaginative reconstruction. Nonetheless, in line with the revival of neglected women in antiquity, she is given 2 pages in Kehlinger's General History. And that common and convenient view which dismisses Theon's works as pedestrian, and second-rate attempts to pick out the more interesting parts of them and ascribe them to Hypatia. Point 10. Following the initial stage of recovery, where the aim was to point out Hypatia's status and relative neglect as a mathematician, Zielska's work has been well received as perhaps marking the start of a second period in the study of women mathematicians, still rather in its infancy. An attempt to place them in a historical context, even when that. 9. Neoplatonism was not simply a revival of Platonism, but had elements of mysticism. As such, it played a semi-religious part in the late Roman Empire. 10. For these and similar arguments see Knorr, who also suggests that, since Diophantus's Arithmetica as it survives contains comments, the edition itself in the form we have it may have been prepared by Hypatia. Doubts are expressed by Cameron. Context is remote and offers few opportunities for identifying role models. An assessment of her life and works, if any, can be reliably ascribed to her, while sympathizing with her difficult, ultimately tragic situation, is not dependent either on approving her obvious ability and charisma, or on disapproving of the elitism, and that belief that the state would be better off if run by philosophers, which she shared with other Neoplatonists. Appendix A. From Heron's Metrics. Introductory note. The standard translation has been changed so that there is as little as possible a modernization of Heron's language, and no explicit algebra. This is more difficult than one might imagine, since Heron does think of lengths as numbers, and multiply them. This happens in the first part. In the geometric proof, the kind of straightforward and perhaps oversimple statements I have made about Euclid. Areas of rectangles are just areas, not products of the lengths of sides, etc., are no longer clearly true, and it is possible that something like algebra, of an embryonic form, was in Heron's mind even if you cannot see it on the page. Prepositions like con and by indicate areas of rectangles or multiplication, and it is unclear which is being used. Most unexpectedly, the on ABC means the product AB times BC, not the area of a triangle. There is a general method for finding, without drawing a perpendicular, the area of any triangle whose 3 sides are given. For example, let the sides of the triangle be 7, 8, 9 units. Add together the 7 and the 8 and the 9, the result is 24. Take half of this, the result is 12. Take away the 7 units, the remainder is 5. Again take away from the 12 the 8, the remainder is 4. And then the 9, the remainder is 3. Multiply the 12 by the 5, the result is 60. And this by 4, the result is 240. And this by 3, the result is 720. Take the side of this, and it will be the area of the triangle. Since 720 does not have a rational square root, we shall reach a difference close to the root as follows. Since the square nearest to 720 is 729 and it has a root 27, divide the 27 into the 720, the result is 26 and 2/3. Add the 27, the result is 53 and 2/3. Take half of this. The result is 26, 12, 13. Therefore the square root of 720 will be very near to 26, 12, 13. 426, 12, 13 multiplied by itself gives 720, 136, so that the difference is a 36th part of a unit. If we wish to make the difference less than the 36th part, instead of 729 we shall take the number now found 721/36, and by the same method we shall find a difference much less than 136. The geometrical proof of this is this: in a triangle whose sides are given to find the area. Now it is possible to draw a perpendicular and calculate its magnitude and so find the area of the triangle, but let it be required to calculate the area without drawing the perpendicular. Let the given triangle be ABC and let each of AB, BC, CA be given, to find the area. Let the circle DEZ be inscribed in the triangle with center H, and let AH, BH, CH, DH, EH, ZH be joined. Then the BC times EH is twice the triangle BHC, and CA times CH is twice the triangle AHC, and AB times DH is twice the triangle ABH. So the perimeter of the triangle ABC times EH, that is, the of the circle DEZ, is twice the triangle ABC. Let CB be produced, and let BF be made equal to AD. Then CBF is half the perimeter of the triangle ABC because AD is equal to AZ and DB to B and ZC to CE. So CF times EH is equal to the triangle ABC. But CF times EH is the side of the on CF times the one on EH. Figure 9 Figure for Heron's theorem, Appendix A. This is the point at which we stop being able to think geometrically. The formula is that CF to EH equals CF EH. But while the left-hand side is a rectangle, the right has arisen by taking the product of two squares and extracting the square root. From now on, numbers whose dimension is 4 seem to come into the calculation. So the area of the triangle ABC by itself is the area of the on FC by the on EH. Let HL be drawn perpendicular to CH and BL perpendicular to CB, and let CL be joined. Then since each of the angles CHL, CBL is right, a circle can be described about the quadrilateral CHBL. Therefore the angles CHB, CLB are together equal to 2 right angles. But the angles CHB, AHD are together equal to 2 right angles because the angles at H are bisected by the lines AH, BH, CH, and the angles CHB, AHD together with AHC, DHB are equal to 4 right angles. Therefore the angle AHD is equal to the angle CLB. But the right angle ADH is equal to the right angle CBL. Therefore the triangle AHD is similar to the triangle CBL. So as BC is to BL, AD is to DH, that is as BF is to EH, and interchanging as CB is to BF so is BL to EH, that is as BK to KE because BL is parallel to EH. And putting together, as CF to BF, so is B to EK. And so the CF to the CF by FB is as the BEC to the CEK, that is to the E. For in the right-angled triangle EH has been drawn perpendicular to the base. Therefore, the on CF times the on EH, whose side is the area of the triangle ABC, is equal to the CFB times the CEB. And each of CF, FB, B, CE is given, for CF is half the perimeter of the triangle ABC, and BF is the excess, by which half the perimeter exceeds CB, and B is the excess, by which half the perimeter exceeds AC, and EC is the excess, by which half the perimeter exceeds AB, since EC is equal to CZ, and BF to AZ. Since it is equal to AD so the area of the triangle is given. Exercise 9. Check through the calculation of the square root of 720. What method is Heron using for finding it? Figure 10 picture for Appendix B Earth at E, Sun on circle center Z. Appendix B. From Ptolemy's Almagest. Note. As already stated, lengths are in sexagesimals with the radius of the circle set equal to 60. The 60ths are denoted by a small letter AP, corresponding to the degrees sign for angles. In order not to neglect this topic, but rather to display the theorem worked out according to our own numerical solution, we too shall solve the problem, for the excenter, using the same observed data, namely, as already stated, that the interval from spring equinox to summer solstice comprises 94 days. And that from summer solstice to autumn equinox 92 days. Let the ecliptic be ABGD on center E. In it draw two diameters, AG and BD, at right angles to each other, through the solstitial and equinoctial points. Let A represent the spring, B the summer, and so on in order. Now it is clear that the center of the excenter will be located between lines EA and EB. For semicircle ABG comprises more than half the length of the year and hence cuts off more than a semicircle of the excenter, and quadrant AB comprises a longer time and cuts off a greater arc of the excenter than quadrant BG. This being so, let point Z represent the center of the excenter, and draw the diameter through both centers and the apogee. EZH point 11 with center Z and arbitrary radius, draw the sun's excenter KLM, and draw. 11. The apogee is the point at which the sun is furthest from the earth. From the picture, this is where the excenter cuts the radius EH. Through Z lines NXO parallel to AG and PRS parallel to BD. Draw perpendicular TY from to NXO and perpendicular KFQ from K to PRS. Now since the sun traverses circle KLM with uniform motion, it will traverse arc K in 94 days and arcade KL in 92 days. In 94 days its mean motion is approximately 93.9 and in 92 days 91.11. Therefore arc KL equals 184.20 and by subtraction of the semicircle NPO, arc N plus arc LO equals 4.20 so arc New York equals 2 arc N equals 4.20 and Y equals CRD arc New York equals 4.32, where the diameter of the excenter is 120. Remember that our tables deal with a circle of radius 60, diameter 120. And EX equals T equals Y equals 2.16. Now since arc N PK equals 93.9 and arc N equals 2.10 and quadrant NP equals 90, by subtraction, arc PK equals 0.59 and arc KPQ equals 2. Arc PK equals 1.58. So KFQ equals CRD arc KPQ equals 2.4 and ZX equals KF equals KFQ equals 1.2. And we have shown that EX equals 2.16 in the same units. Now since EZ equals EX plus CX, EZ equals 2.29 where the radius of the excenter is 60. Therefore the radius of the excenter is approximately 24 times the distance between the centers of the excenter and the ecliptic. Solutions to exercises. 1. If is on the two curves, then x equals x equals x, y equals 2a, so x equals a at 2. The description of what Menaechmus did does not read quite like this. For a plausible version, see nor. If you replace 2 by m in the equation of the hyperbola, then you solve the problem of increasing the volume by m. Similarly, 2. Suppose C and D are constructed. Then, A, B equals. The three ratios in brackets are equal, so this is. If B, A equals m, then is m. So, is m. 3. Straightforward, the radius is the height of the equilateral triangle whose side is the side of the hexagon. So by Pythagoras' theorem, the side is 3 times the radius, and the perimeter of the hexagon is 6.r equals 4r. 3, 4. This depends on Euclid 6. 3, which you may not know. This says that in triangle ABC, if AD bisects angle A and meets BC at D, then AD, AB equals BD, AB. In our case, this gives A, B equals AA, C. Manipulating ratios, A, B equals A, B plus C as required. 5. In the picture, CDOE is a square, so all of its sides equal R. Hence, AE equals BR, BD equals AR. But by the property of tangents, this means that AF equals BR and BF equals AR. Hence, AB equals AF plus FB equals AR plus BR, and the result follows. From the factorization, equals 35 equals 6, so A plus B equals 41. This is why we square 41 and get equals 1681. But also the area SR equals 35/6 is equal to 210, and this is by a different. Figure 11. The figure for exercise 5, with BC equals A